Welcome. This video is going to look at the topic 5 tests that we had over energetics. And as I move through the 9 multiple choice here, I'm going to try and focus on how you're supposed to be able to do these without a data booklet, without a calculator, and in a minute and a half. Number 1 said, what is the energy in kilojoules released when 1 mole of carbon monoxide is burned according to the following equations? So notice it's supposed to be in kilojoules. It's for just 1 mole. So the idea here is that you have to realize the equation's written for 2 moles of carbon monoxide. So you need to cut this value in half, and given the values you've given, even without a calculator, you should fairly quickly be able to realize B is the correct choice for number 1. Number 2 wants to know which processes have a negative enthalpy. Negative enthalpy means it's exothermic or it's releasing energy. So what you're supposed to do is look at these 3 equations and determine what's going on in each one. In 1, when you see that O2 is one of the reactants, that means that this is a combustion reaction, and that is always exothermic. That's the whole point of a combustion reaction. Number 2, you see HCl and NaOH. That's your hint that you've got an acid and a base. So that's a neutralization, and that too will be releasing energy. And then the third one is a physical process. You're going from a gas to a liquid. So if you think about it, the particles need to slow down. And when you slow down, then yes, you release energy. So D would be the correct choice here, 1, 2, and 3. Number 3, a pure aluminum block with a mass of 10 grams is heated so its temperature increases from 20 to 50 degrees, or a change of 30. The specific heat capacity of the aluminum is 8.99 times 10 to the minus first joules per gram per Kelvin. Remember, Kelvin and Celsius degrees are interchangeable, so we can just as easily think of this as being per Celsius degree. So which expression gives the heat energy in kilojoules? So my mass is 10. My specific heat is 8.99 times 10 to the minus 1. And my temperature change is 30. So D would be the correct choice here. So question number 4 is more difficult than it appears. You have to be careful as you're doing this one. It says you have 100 centimeters cubed of 1 molar HCl, 100 centimeters cubed of 1 molar NaOH, resulting temperature change of 5. What will be the temperature change when 50 centimeters cubed of each of these are mixed? Well, in both cases, we are looking at M times C times delta T, or MCAT, to yield delta H. And I think most of you realize that if X was the heat released in the first scenario, then you should have 1/2 X when you cut the amounts in half. So in the first scenario, I had 200 total centimeters cubed, or 200 grams of solution, times 4.18, and I had a 5-degree temperature change. So in the second scenario, if I've cut that in half, I have 100 grams times 4.18. If I want X to be half as much, I've already cut this variable in half, so that means my temperature change is going to have to remain 5, because if that goes down to 2.5, now all of a sudden I only have 1/4 the temperature change. And that is not the case. It should be half, because I have half the reactants, half the collisions, half the product being made. Number 5 then, which type of reactions are always exothermic? Again, from what we talked about on the previous page, neutralization, combustion are always exothermic reactions. They're always taking less stable products and creating more stable products, so heat is going to be released. Decomposition, on the other hand, is mostly endothermic, or mostly not exothermic, because you're breaking down compounds, and when you break compounds down back into their elements, oftentimes that is an endothermic process. So decomposition can be either one. It's not always exothermic by any stretch. So B, 1 and 3 would be my correct choice. Number 6, they want to know which statement is correct given the enthalpy level diagram below. So before I even look at my choices, I would take a look at the diagram here, and I remind myself that energy is the y-axis, the reactants are the left, the products are the right, the plateau is there. And so I can see that P is lower on the energy scale, so it means it's exothermic. The products are more stable, they take less energy, energy is being released. So as I read through these choices, the one that fits that is B. The reaction is exothermic, energy is given off, as we see, and the products are more thermodynamically stable than the reactants. Number 7 is somewhat similar. They want to know which is correct about energy changes during bond breaking and bond formation. So if we think of the same energy level type diagram, we see that as you go from reactants to the transition state, so that's this space right here, energy has to be put in, and so delta H is positive, and that's where the bond breaking takes place. On the other side then, as the products are being formed, that's bond making and energy is being released, or delta H is negative. So when I look at that, that would fit with C, endothermic, and delta H is positive during the bond breaking, and during bond formation, it's exothermic and delta H is negative. So C would fit both sides of the graph. Number 8 wants to know which equation best represents the bond enthalpy of HCl. So we're looking for a net change of one HCl bond from my reactant side to my product side. And A looks like it fits the bill, except that it results in 2 ions being formed, not atoms. So that's a different level of energy. It takes a certain amount of energy to ionize hydrogen. So A is not acceptable. B, that is truly just one HCl bond being broken. C, half H2 and half Cl2, that doesn't count because H2 and Cl2 each involve a single bond, so there's energy involved there. And the same problem resulting with D, you're actually breaking 2 HCl bonds and you're forming the H2 and the Cl2 bonds. So in C and D, it doesn't matter if you're looking at half the H2 and half the Cl2 bond or at the whole H2 and the whole Cl2 bond. Either way, you're looking at another bond, so that is not the net energy for just the HCl bond. In number 9, consider the following reactions. What is the value of delta H in kilojoules for this reaction? So looking at this reaction, I see that I need Cu solid. So I see that this needs to flip over. So I change my sign from positive 11 to negative 11. And then the CuO up here is in the correct direction. So I can leave that at the direction it's running. And then I just need to make sure that I'm going to end up with just one CuO. But I will, because when I flip this one over, this is instead going to be CuO plus Cu yields Cu2O. And so now this is going to reduce to just one of these. My Cu2O is going to cancel out, and I will be left with the equation I was interested in. Cu plus half an O2 yields CuO. So I left the first equation, which leaves me the negative 144. I need to flip the second one, which leaves me a negative 11. And so the only answer that represents those two values is C. I'm not quite sure why IB doesn't really list this as negative 144 plus a negative 11. That really would be more precise for what's happening, but mathematically it means the same thing. So as we move into number 10, our data unfortunately is at the bottom of this page, and then the work was on the following page. But you notice we have an initial and final temperature of water, and because they tell you it's water, that means I should be using the mass of water, and I should be using the C value for water. And again, don't fall into that common mistake of using the mass of your fuel burned. That's going to help us calculate the moles and eventually give us the kilojoules per mole. But it's 100 centimeters of water, and that's the temperature change we're looking at, and that's the C value we're using. So that's the mass we have to use. So moving on to the next, use the data to calculate the heat evolved when the ethanol was combusted. I used the 100 grams of water times 4.18 times the 35-degree change for water, and that gives me 14,630 joules, or I could express it as 14.6 kilojoules. They didn't specifically say to express it as joules or kilojoules, so as long as I label my answer correctly, either one is fine. Same with 2, they want to know the enthalpy change of combustion per mole of ethanol, so I can express this as joules per mole or kilojoules per mole. That means I need to take the 1.78 grams and divide by the molar mass of ethanol, which is 46.08, and they had given you the formula for ethanol, or I gave you the formula for ethanol, so that shouldn't have been difficult. So the 0.0386 moles was your first mark, and then I take the total heat gained by water, because my assumption is delta H for the water is the opposite value of delta H for ethanol, and that's why I would make my final answer a negative value here of negative 378 kilojoules per mole, because the water gained that heat, which means the ethanol lost that heat. Two reasons why the result is not the same as the value in the data booklet. Heat loss and incomplete combustion were common reasons you gave, and those are good, easy ones to give. The copper calorimeter absorbs some heat. That's another good one. A couple of them that you put that don't fit here is because bond enthalpy is an average. We weren't using bond enthalpy in this. We were looking at the heat of combustion that's been found and verified experimentally to our experimental values. So you have to make sure your reason fits the data you're working with. Number 11, define the term average bond enthalpy. So there's really three things here. First of all, and it was worth 2 marks. So if you had 2 of these 3, you got both marks. First of all, you have to realize that anytime we're talking about bonds, we're talking about a whole mole of bonds. So it's the energy to break 1 mole of bonds. Second thing is with bond enthalpy, it has to be in the gaseous state, so it's only the bonds that we're dealing with and we're not overcoming intermolecular forces. And then the word average was used because it's average for several compounds with the same bond, containing the same bond. So those were the 3 points that you needed to make 2 of to gain your 2 marks. Part B was worth 3 marks, and so what I looked at this was for several things to see, did you have all the bonds you needed? Did you realize it was reactant minus product? And did you come up with the right answer? And surprisingly, very few of you actually got to the correct answer. It was really easy for you to miss marks. The only way C4H8 results in a balanced molecule is if you have a double bond in there somewhere. Now, I put my double bond between the 2 middle carbons. It doesn't need to be, but that's where I put mine. But carbon needs to have 4 bonds. So if it's double bonded with carbon and single bonded to 2 other carbons, it just needs 1 more hydrogen. But those end carbons, they need to have 3 hydrogens. So you had to make sure your structure used 4 carbon, 8 hydrogen, and all 12 atoms were stable. O2, most of you knew, was a double bond. CO2 is 2 double bonds. Most of you, H2O consists of 2 single bonds. So by far the problem people had was figuring out their HCH bonds, that there was 2 carbon-carbon single bonds and a carbon-carbon double bond. But I've summarized mine here as far as the bonds, the type and number of each bond I added, and then here I've subbed in the values, the correct values for each one. And that's what resulted in my final answer of negative 2082 kilojoules per mole for ethanol. Number 12, I gave you another shot at bond enthalpies. And again, a lot of people did not draw the structure correctly. N2H4, if you count up your electrons, nitrogen each bring 5 valence electrons for a total of 10. The hydrogen makes it 14. So when I bond this, I would only need a single bond between the 2 nitrogens because I've got 2, 4, 6, 8, 10 bonds being used in the structure. But each of these nitrogens would also have a lone pair on them. So I don't need the double bond. I need to leave the nitrogen single bonded so those 2 lone pair have a place to go. So knowing that, I have 4 NH bonds and 1 nitrogen single bond along with the oxygen double bond in my reactants, and those are the values that I've put here. And then on the other side, nitrogen always triple bonds to itself with a lone pair on each nitrogen. And then I would have the 4 OH single bonds, so those are my values here, resulting in negative 581 kilojoules per mole. Now, more people did get this one correct than the previous one, but bond enthalpy, the hardest part by far is figuring out what all of your bonds are. And then number 13, the standard enthalpy change of 3 combustions is given below, and you're trying to get this reaction. So when I take a look at my first reaction here, C2H6 is a gas. So I can see that this is the correct direction, but it appears I'm going to have to cut it in half. So that's why I put leave in half. So the negative 3120 is still going to be negative, but it's going to be half that value. The H2O2 yields 2H2O. The H2 is what I need, and I need it on the other side. So now I think I'm going to have to flip this equation and probably cut it in half. So this is going to be a positive 572, but half that value. And then C2H4302, that also needs to be flipped, but it appears to be the correct value. So that's what I think I'm going to do with each equation. If I scroll down here, then I actually did those things. I left my first equation, but cut it in half, as you can see, as I've written right here. The second one, I flipped it and cut it in half. And the third equation, I've only flipped. And when I do that, that does yield the equation I wanted, because as I look here, I've got C2H6 in one place only. The 3.5 O2 is canceled by 3 O2 and half an O2, so that no longer carries through. The H2O, I've got 3 H2O here, and then I have H2O and 2 H2O, so that also cancels out. The 2 CO2 cancels out. And so this is actually an arrow here, not, oops, I got the highlighter there, but try that again. I guess it's not going to let me erase that, but this is the arrow here. And I end up with what I've canceled then is just H2 and C2H4 left. So when I add this up, positive 1372 kilojoules per mole should be my correct value.